Hello, everyone, and welcome to this month's Department of Energy Python Exchange. My name is Cameron Riddell, and I will be your host this evening, or afternoon, or morning, all depending on the time zone that you live in. As you all may know, our goal is to have Python thrive within the National Lab System and associated research sites. In support of that goal, we are joined today by guest panelist Emanuele, who works on control system interfaces of a particle accelerator that he works in. And he will be sharing how he uses Python and Jupyter in his work environment so that we can all better leverage those tools in our own work. But before we get into the agenda and introduce all of our panelists today, I want to remind everyone of a few key points about these exchanges. This call will be recorded, edited, and posted online. As a consequence, please be conscious of the information and the questions that you may ask to ensure that you're not accidentally sharing anything that is privileged or requires clearance. Additionally, as you all know, we are a growing community and we would like to stay in touch with each of you. If you would like to be kept up to date with our monthly exchanges, please sign up for our mailing list, which you can find on our website, meetup.doepy.org. You can additionally find recordings of all the past exchanges on this site, as well as a recording of today's exchange once it has been edited and posted. For those of you who have never joined us for an exchange, I would like to share with you that these exchanges are typically broken down into 4 parts. First, we'll introduce our fantastic lineup of host and guest panelists so that you may all get to know them, as well as their respective fields and backgrounds. Second, we'll kick off into a coding activity where we'll ask some very applied questions to our panelists to elicit some practical discussion about best practices in software development, Python, and where they fit into the world of academic and scientific research, because we're not all software developers. Third, we will turn things over to our guest panelists who will share some prepared remarks on Python as well as his work and how he integrates it. Then to wrap up, we will have a full discussion about the points brought up by our guest panelists, by Emanuele, and for everyone joining us in the audience, this is your chance to ask questions and engage with our panel to help us all understand where Python fits into the life of a researcher. First up, if you would like any more information on our guest panelists or what we're aiming to accomplish here today, you can always check our website. That's meetup.doepy.org. And for our host panelist lineup, we have myself. Hello, everyone. I am Cameron Riddell, and a common question that we ask each of our panelists is, what do you consider yourself an expert in, and what types of questions are you here to answer today? Well, I don't consider myself to be an expert in much. I have a background, surprisingly, in psychology, where I used to study human memory, and I love fielding questions, anything that has to do with Python, NumPy, Pandas at Scientific Stack, or Matplotlib. Those are my absolute favorite types of questions to answer. Next up, we have our host panelist, James Powell, who's affiliated with NumFocus. James, what are you an expert in, and what types of questions are you here to answer today?
I feel like one thing that I am maybe not a unique expert in, but I'm pretty good at is understanding APIs behind data management tools like the Blue Sky Project's Blue Sky. If you're using a tool like this at your light source and you want a little bit of additional guidance outside of what Tom and Dan can provide you, I think I have a pretty good handle of why these things are built the way they are. And if you want to build your own tools and you're curious, how do I learn lessons from these effective tools to build my own APIs? I'd love to answer any of those questions for you.
Thank you very much, James. I'm excited to have you here with us today. Next up, we have Dan Allen from the Brookhaven National Laboratory. Dan, what are you an expert in, and what types of questions are you here to answer for us today?
Yeah, I'm not sure I'm an expert in much of anything, really, but I'm trained as a physicist and have spent the last 7 years doing software development in the service of science, and happy to answer questions about building collaborative open source projects in a way that helps everybody get along and does something useful in a distributed way.
Absolutely. Thank you so much, Dan, and thank you for your humble opinion. I'm sure many do consider you an expert. We're also joined by host panelist Matthew Carbone. Matt, what do you consider yourself to be an expert in, and what types of questions would you love to field for us today?
Hi, everyone. Well, like Dan, it's the word expert's a little it's a little tough, feels a little weird, So, but my training is in theoretical condensed matter, and I do a lot of data-driven science. So, if you have questions about numerical scientific computing, machine learning, those types of things, then I can help with that.
Fantastic. Thank you so much for joining us today, Matt. And moving right along, we're also joined by host panelist Tanny Chavez. Tanny works at Lawrence Berkeley National Lab. Tanny, what do you consider yourself an expert in, and what types of questions would you love to help us answer today?
Well, my background is in machine learning and data science per se, and I really enjoy questions on how we can share tools like this or algorithms with a vast diversity or majority of scientists in different areas. So that'll be most interesting in hearing about.
Fantastic. Thank you so much, Tanny. I'm very excited to hear your comments on what Emanuele has to share with us today. Now, we do have one more host panelist. We cannot forget about one of my favorite host panelists. They're all my favorites, of course, but we're also joined by Tom Caswell. Tom also works at BNL, along with Dan and Matt. We are joined by one more panelist with us today, and this is Jan Janssen. And now, if you have attended our past exchanges, Jan was actually a guest panelist with us, and today we invited him to be a panelist up on stage here with us. And so, Jan, I am curious, what brings you to these exchanges, and what do you consider yourself an expert in, and what would you like to help us answer today?
Yeah, thank you very much for the introduction. I guess what brings me here is definitely the exchange, the collaborative environment that we experience at the labs, and also now beyond the labs, working on Python together. And I would say my own expertise, currently I'm very much looking into the MPI4Py package and really running Python programs on a parallel scale. And the other expertise is building complex workflows with a Python package that I developed, and then packaging Python modules using the CondaForge package managers. So those are the three parts I would see myself as.
Absolutely. And thank you so much for all your work and effort you do contributing to open source and building packages for researchers to use and make their lives easier. We all truly appreciate it. Now, our guest panelist, who I've already shared with you, is Emanuele Laface. Emanuele joins us from Lund, Sweden, where he works at the European Spallation Source facility. Emanuele, what do you consider yourself to be an expert in, and what types of questions would you like to hear today?
Hello, everyone. I am expert, I think so, in particle accelerators, and in particular, I am a specialist in modeling electromagnetic device to accelerate and focus proton beams, especially for hadrons machine. But in the last couple of years, I built from scratch a particle accelerator. So I end up in solving any kind of physics problem, especially from the point of view of the control room. This means quick and accurate problems through coding or modeling in complex environments. This is more or less my skill. And about question, everything that is from the physics to the control of a particle accelerator, for me, it's very interesting.
And Emanuele, I'm curious, how often would you say you write Python?
Every hour, every day. I definitely write Python all the time. From little problem, from solving mathematical problems, so even symbolic calculation, to numerical and very detailed data analysis. All the chain, let's say, it's a daily job.
Fantastic. That is great to hear. And I think that should mean that you will have no problem with our upcoming game that James is preparing to present. For those of you in the audience who are unfamiliar, we always do a little coding game so that we can get our panelists all talking Python, sharing some of their thoughts and opinions on what is a best practice and why is it a best practice, and should I even care about a best practice? So James, I will turn things over to you to play our game for today.
So today we have another coding activity ready for you. This coding activity is called When Do I Want? I'll share my screen with you and we'll jump right into it. And so you should now see my screen and I'll explain to you the rules of the game. When we are teaching scientists how to use Python, we're teaching them an enormous number of details. Oh, you need to be able to write functions with this and this syntax. And in Python 3.10, there's this new syntax. In 3.11, there's this even newer syntax. And we're just overwhelming them with all the things they have to learn, all the things they have to know. And so I wanted to do a little activity where I present each one of our panelists with a couple of things that you might want to put in front of a scientist, or they may have seen as part of their learning of Python, and answer them a question of, oh, you want to do that when, ... or don't worry about it until ... This is a relatively short game. We'll go through just 5 quick rounds. I'll start us off. Host panelists, feel free to jump on audio as you see fit. The very first question is, you teach the scientist, look, Python has dictionaries and sets and tuples and lists. And they come to you and say, when do I want a set or the tuple or the dictionary or the list? You gave me 4 things. I don't even know when I want one of those things.
I'll kick things off, James. For one, I am a little offended you didn't put the parentheses around the tuple. It works all the same, but when would I want to use a set or a tuple? Well, mechanically, I can speak that the set, right, is an unordered list, or unordered collection, I should say, of unique objects. And so maybe I'll want a set when I don't care about the ordering, but 2, I'm only interested in non-repeated, unique-only values.
Matthew, did you want to chime in with when you want the set or the tuple, or maybe the dictionary or the list? 4 options. They got to pick one.
Sure. I can throw in a comment about the tuple. It's immutable, so once you make it, you don't get to change it. So if you want to, have a dare I say, a set of values, but I don't mean set in the proper sense, but I can't. There's like no way to describe without talking about some other Python object, right? But just a grouping, right, of objects in one bigger group that you can't change. That would be another reason to use a tuple.
Good. Any other host panelists want to give this a try, or shall we move on to the next round?
Well, I would say that
first, Emanuele.
Oh, thank you. I would say that the dictionary is, for me, quite different from the other because you have the possibility to browse it through the keys. So you don't have to, if you want to get one of the elements, you can use in a clever way to retrieve it using the keys. So it's quite different set for me.
So every time you want some kind of lookup or you have 2 pieces of data where one is used to look at the other?
Yeah.
Jan, did you have a comment that you wanted to share?
Yeah, so in similar direction. So I would say you can even use a dictionary for points where many people would start to write the first classes in the examples, right? So because the dictionary is so versatile, in many ways, it's easier to just store it as a dictionary rather than starting with your own class and building all this infrastructure. So I'm a big fan of the dictionaries in Python.
So maybe for simple data structuring, don't do all the complexity of a class. Don't worry about that just yet. Focus on maybe tuples, name tuples, and maybe. Let's take a look at our next round. When do I want NumPy or Xarray? You already showed me lists in Python. I can store data in that. When do I want these 2 tools? And especially some of our Xarray users, I think would be very helpful to answer, when do I want Xarray and not NumPy?
I think whether it's necessary to be labeled or not. So if something within these n-dimensional arrays is relevant to have or to integrate the labels within them. For example, let's say a time series dimensional array. In that case, the next array will be a little bit more, it will be a lot more suitable for that type of data, but it will only, in my opinion, it will come down to what we're trying to store and how we like to access it.
I'm curious, Danny or our colleagues at BNL, are there situations when Xarray isn't strictly better than a NumPy array?
So if you don't have an index that has meaningful values in it that aren't different than the bin position, then a NumPy array is as good as an Xarray. However, if you know what your dimensions of your array are, and want to be able to select on those values, an X-array is much more powerful.
Tom, what's a common situation where an X-array data array will really improve somebody's interaction with their data, where a NumPy and D array will leave them confused? What's a simple example?
I mean, the strongest example for X-array is going to be geospatial or climate data, where your dimensions are latitude and longitude. And if you ever ended up accidentally transposing that and it's just a NumPy array, you could add an n by m array together to another n by m array, and the data isn't going to, you're going to get nonsense because you just added the wrong things. Whereas an X-array can know which one's lat and which one's long, it will make sure it's added correctly. Similarly, if you want to resample on an external coordinate system, X-array has very nice tools for doing that resampling in a way that you'd have to write a significant amount of code on just a straight NumPy array to manage yourself.
Anybody want to chime in with any possibilities where an X-array is worse than a NumPy and D array? Or is it the case where it's just not that much more useful?
I think it's heavier in terms of the things you need to import. X-array depends on pandas, and it takes a long time to install that and some time to import it. So NumPy is going to be faster and lighter. It's conceptually lighter, which also helps. More people have heard of NumPy and are more comfortable with it than X-array. And finally, it's more portable. If you send an X-array into Matplotlib, it will convert itself into a NumPy array. So at least it's interoperable. X-array is interoperable with anything that can take NumPy, but it interoperates by just sort of downgrading itself into a NumPy array. And if you're mostly going to be working with scikit-image or scikit-learn or Matplotlib, at least as these things are written now, you might as well work with NumPy array because that's what they're going to see.
Cameron, go ahead, Emanuele.
There is also the other fact that NumPy is very well established in many other libraries. So, for example, when you interact with other code like C or Java or whatever, many of those comes out with structures that are NumPy in general, or when you get the data from another code. So maybe also in terms of compatibility with other tool, NumPy in general is much more used.
And Cameron, any final thoughts on this? Maybe when you do not want a NumPy array, maybe if the data is growing, what do you think?
I mean, when you're dealing with growing data, you're going to run into issues with both of these because they don't append well. And what all that means is when you want to grow a NumPy and D array, you can't actually grow it kind of in the canonical sense. You actually have to over-allocate a new NumPy and D array, copy all of the old data in, and then add in your new data in and append operation. So when I'm dealing with growing data, I would reach for something like a Python list. It's a little bit more optimized for growing in size and resizing itself.
Perfect. Let's move on to round 3. When do I want to write a function? I mean, I'm good enough at just cutting and pasting things, making my scripts really, really long. Matthew, when do I actually want to write a function?
Whenever you have to reuse code. That's the zeroth order answer, right?
Very good.
I'll also add, I like functions because they're so easy to document, so I can always remind myself 10 days from now what this thing is doing. But yeah, I mean, the general answer is when you need to reuse code, right? You have an operation that takes in some inputs and gives you some outputs, or even does something in place, right? And you want to use it more than once, then a function is the way to go.
Here's the counter question. That sounds easy enough. When do I not want to write a function? I know when I want to write a function. Are there cases when I don't want to write one? Panelists?
Yeah, maybe you don't want your functions to be too small. So some people have the tendency to break down things to very small objects and have like 10 different functions which do more or less the same, just return slightly different data types. So sometimes I feel it's like make a function that has a clear input and a clear output, and then reuse this function rather than writing additional functions which more or less do the same.
Yeah, I would go along the same way, and I would not write a function when you need a class, for example. There are some programmers that tend to put everything in one big function with a lot of, from the fact that in Python you can return whatever you want, and you don't have to specify in the beginning. There are people that tend to write everything in a function and then return very different things in a weird way. So I would refrain from this.
Kenny, Tom, any other comments on when to or when not to write a function?
I tend to write a function the third time I reuse the code.
Okay, very good. Nice little rule of thumb there.
Yeah, the
Anyway,
first time that Emanuele?
So the first time is just, I wrote it because I needed it. The second time might just be chance. The third time it's worth, making a function and reusing it.
Kenny, any comments, or shall we move on?
No, besides just adding maybe also the thought that if I see that there is a piece of code that most likely is going to change, either a certain amount of for my next development, for example, or like within a couple months, maybe I would like to elaborate more on that aspect. So even though maybe I'm not reusing it at many points, I know that it's going to be changing quite a bit throughout my development. So for that reason, I'd rather have it somewhere else, so I can refer to it.
So there we go. It's about establishing a single source of truth that you can change in one place and it changes everywhere. Fantastic. Let us move on to our fourth and almost final round. Great, we're writing functions. But what about this thing that you just taught me about, the decorator? When do I want to write a decorator? And when do I want to use a decorator that somebody else wrote? I thought functions were hard enough. Now you're telling me things that apply to my function to return brand new functions?
So I tend to use the same rule of thumb, that if I need to do something once, I'll just put the code at the top and bottom of that function. Typically, if you're using a decorator lets you add logic before and after the body runs. So if I just need it once, I'll just put them in that function. The second time, I'll start to think about it, but probably not worth the overhead of actually making one. And the third time, I've copy and pasted the same code 2 places. Then I make the decorator and go back and refactor.
Sounds like every time you're writing lots and lots of functions that look kind of similar, you're going to reach for that decorator. That's a good start. Cameron, did you have something to add?
Yeah, I think that's what Tom said is 100% accurate. Something I would add is I tend to think about decorators as having access to different entry points in your code. So when I apply a decorator, I can execute some code when I define a function, or I can execute code before or after that function is run by returning a wrapper. And so maybe if I want something like a registration pattern, and if you've ever used Flask, you've seen this with the @app.route and other common metrics, things like PyTest also use decorators in this fashion, where all we're doing is we attach this decorator to a function, and we're just registering it to some central location so that we can automate the call of that function, something like you would do with PyTest. And so that's one of the registration use cases. As for before and after a call, you can manage external resources, set up teardown, anything you might want to do before a function is executed, or any boilerplate, I should say, you want to do before or after a function is executed.
Jan, Dan, any final thoughts on when to write a decorator or when to make use of somebody else's decorator?
I think they covered it.
Very good. Okay, let us move on then to our final round. Okay, you told me about functions, you told me about decorators, but then you showed me this thing called a generator. When do I want to write a generator? And for bonus, when do I want to write what Tom likes to call a generator coroutine, where the yield is an expression and you have an equal sign to the left-hand side of that yield?
When you have a sequence and you want it to be someone else's problem to decide how long that sequence goes.
Okay, when you want to externalize the computation, or at least the modalities around completing that computation, very good.
And also the memory, right? So if you have a function that produces large objects and you don't want to store them all in memory, then I would go for the generator.
Okay, so if you are producing a large output data set, but you only need to look at one element at a time, you don't need to do it all at once. You could use a generator and then loop over each element at a time. Good. Everybody want to talk about when to write the equals yield generator coroutine, as Tom likes to call them? When you're using Blue Sky as an answer, because I think you don't really have a choice in Blue Sky. That's the name of the game.
I guess riffing off the blue sky answer, when you have some kind of adaptive process where you have two-way communication and you want to structure your program to separate the thing that's receiving the data and doing something with it and then sending it back out. It's a really nice model, and it makes the flow easy to read on the screen compared to solving the same problem with like a class.
To expand a bit on what Dan said, I think where it really shines is when you have a program that looks like it could be split into two loops, both of which are the one that's quote unquote in charge. And the classic case where coroutines were introduced were for the case of parsing a text file. You could view this as you have a loop that's reading bytes, and then that's the primary loop, and then as a subsidiary activity is parsing them to understand what the bytes mean. Or you could view this as the loop that's parsing the file, and that the parsing loop is the one in charge, and then as a subsidiary activity, you're calling some function to get the next bit of bytes. And anytime you have this ambiguity where you're not sure which one should be the caller and which should be the callee, coroutines are really powerful because they let you bring back some of that inherent symmetry to the Python code.
Arguments for symmetry aside, I want to end this last slide with an appeal to the data scientists and the machine learning folks among us, Matthew and Tanny. When you're doing something like training a model, you could train that model for n steps. You could train that model until the model gives you certain outputs. You could train that model for a fixed amount of wall clock time. And all of that ability to control when the training stops is something that you'd have to write in a function as additional arguments. N steps, amount of time, until the model converges to some result. Whereas if you wrote a generator, you could just have the model run forever and then allow your users to decide how they want to control where it starts or stops without you having to do any of the work to decide up front all the different ways they're allowed to start or stop. I am certain that for those of us who think among all of these tools that generators are the rarest thing to see in practice, may actually end up being one of the most common things that we may find in our code. But I believe that brings us to the end of our coding activity. Thank you to all of our host panelists and our guest panelists for participating. If you have any questions about, somebody told me about this thing called a data class. When do I want to use that? Somebody told me about this thing called a context manager. When do I want to use that? Please feel free to put it in the BlueJeans Q&A widget. We can answer it here, or to send us an email. We'd be happy to integrate that into our discussion for next time. But with that said, I'll hand it back to Cameron to continue with our prepared comments from our guest panelists.
Thank you very much, James. The coding activity was absolutely fantastic. I had a blast getting to discuss some of these common things that you encounter in Python, and that really, I don't take 2 seconds of thought half the time, and I really should be putting some more thought into my code before I write it. With our coding activity done, we will now have Emanuele take over and share his comments and thoughts on how he uses Python in his own work. And so, Emanuele, you can go ahead, share your screen with us, and get us started.
Thank you. And you should start now to see my screen. And first of all, I would like to thank Matthias Bussonnier. I hope I pronounced it correctly. That is the guy that puts me in contact with you, because I had a problem with Jupyter. I started to contact him because he was quite expert, and in the end he gave me a workaround, not exactly a solution to my problem, but I will show you this later. Before, I want to introduce my particle accelerator. I say my because I started to build this particle accelerator back in 2011, so it's a long time that I work in the design and the construction of this particle accelerator. This is specifically a spallation source, is the European Spallation Source. There is another machine in the world that is the SNS, the spallation neutron source, and is in Oak Ridge in Tennessee. And this is the second machine that we are building. Why we are building a spallation source? What is a spallation source? Maybe some of you knows, but I want to show you some example of what we are going to do. This is an image of an old camera. Who is old enough can remember that there were cameras with film inside. And if you try to do an X-ray, you will not see if there is a film inside because it's shielded, because the metal shields X-rays. You can increase the power of X-ray and melt the metal, but not see inside. This is because the nature of the material. So with neutrons, you can see an image that is complementary, we can say. You can see a structure that is different because neutrons has a different way to interact with the material. And in this way, you can see the inside of this machine, for example, and you can see the film. So the idea is that the spallation neutron source, or in our case, the European Spallation Source, is a device that generates neutrons, and neutrons are used for imaging. In particular, is a gigantic microscope, very cold also because it's superconducting. This is another example where we have a statue of Buddha that was found during some archaeological sampling, archaeological excavation, and the metallic structure was shielding X-rays. So the researchers here were interested in the inner structure of the object, and was not possible to see inside with the X-rays, while with neutrons it's clear how the object is done. And the same can be applied in objects that are moving, like an engine, because you can generate neutrons in bursts, in shots, because we generate neutrons from protons, and we can control the protons with a particle accelerator. And in this case, you can really see an object moving. You can record a video. One of the goals of our facility will be to have a video of a protein while it's folding. So that's is one of the open problems in biology, for example. And this is another example that is quite fun to show in general, because especially I am Italian, you can guess from my accent, and we use this kind of coffee machine, and it's always interesting to see how devices work. And I always wondered how the coffee is produced here. I know the theory, but to see in real life is another thing. And then when you show this to Italians in general, they complain that the quantity of water is not exactly correct, the coffee is not pressed properly, etc. But you know how picky are Italians with coffee and food. You have to think that anyway is bombed with neutrons, so probably the taste is not that good anyway. So these are a few examples, and as you can see, are quite big objects, because these images were done through a nuclear reactor. So these neutrons that are using in these images are generated from a nuclear reactor, an experimental nuclear reactor in Zurich, in Switzerland. And the intensity of neutrons is not very high. That's the reason why the object is not so, it has to be big, let's say. This is a real case that is done at the Spallation Neutron Source in Oak Ridge. So it's done with the Spallation Source. And in this case, the blade of a turbine was analyzed in 3D with the tomography to be sampled and to show if the prototype of the turbine was done according to the design of the engineers. And with neutrons, you can scan, and because you can decide where to send the neutrons, really, you can do a 3D scan of the object, and then you can reconstruct, of course, and have the images and browse inside. And so this is not a simulation, it's really a reconstruction of the material. And then the engineer can go inside, and here in this case, depending on the color, they can see the thickness of the material or the thickness compared to their project, and see if it was done according to the design, or if there is some parts that may need some rework, etc. So that is the more or less the use of this machine. And today, if you want to do this kind of measurement, you have to apply for it as a lab or as a private company, I think, and wait for 5 years for the measurements, because the queue is around 5 years. And that's why we are doing a second machine in Europe for neutrons. So just to go quickly, because I will talk a lot about particle accelerator, proton accelerator in particular, to do the particle accelerator to generate neutrons, we need to smash protons on a target, because neutrons cannot be extracted easily from some source. Protons are quite easy to generate from hydrogen, and that's what we do in the source. This is the proton source that basically is a bottle of hydrogen that injects into a magnetron, the same device you have in the microwave oven. And then it generates a plasma, and then the platform is charged to 75 kilovolt, and then the protons are extracted and transported along the first line that is called the low energy beam transport. This is how we generate protons, but then we have to accelerate them, because if we send those protons to a target, we do not extract neutrons. To extract neutrons, we need around between 1 and 2 GeV of energy. It means that the total energy of the protons has to be double than its mass in energy, because the mass of proton is more or less 1 GeV. And to do this, we need several devices in the middle. The reason why we have several devices is the same why you cannot run at 1,000 kilometers per hour, or I should use miles because you are all Americans, but I don't know the conversion by heart, so I will use kilometers. And when you want to run 10 kilometers per hour, you can simply run. If you want to go to 100 kilometers per hour, you need a car. If you want to go to 1,000 kilometers per hour, you need an airplane. And this is exactly the same with particles, because the devices to accelerate particle in different regime are completely different. For example, at low energy, we use the radio frequency quadrupole. I will return on this because I have a measurement to show on this. Then we have devices to focus the beam and keep it in the pipe. Otherwise, the beam tends to go everywhere. And we accelerate again with a structure that is we call drift tube LINAC. Is an electromagnetic structure that couples an electromagnetic field in this tube with this little aperture that we call drift. This device was invented by the same guy that discovered that the dinosaurs were killed by an asteroid. It's quite an interesting story. If someone is interested, in the end I can explain. He got the Nobel Prize, but for another thing, the bubble chamber that is used to track particles in the detectors. But he invented also the drift tube LINAC, or a structure that was called Alvarez structure. His name was Alvarez, and his son was a geologist, and he helped him in developing the theory of the asteroids for dinosaurs extinction. Then we have the superconducting part, because to have efficient acceleration, we put everything in a cryostat, the accelerating structure, and then we pump helium. We make this object superconducting, and then we put very high voltage in order to create a gap of voltage that accelerates the protons. And this structure is around 500 meters, and then we smash our protons in the end on the target. We have to paint on the target, otherwise the power that we release, that is 125 megawatt, is too high and we melt the target. So we have a painting system on our target, and the target is a wheel of tungsten where we paint each window, and then we produce the neutrons. The neutrons are then moderated, cooled down, extracted, sent to extraction line that are neutron guides, as we call, and then arrive to the station for the measurement. Now, this machine is a quite complicated device. We estimate in the order of 10 million, 20 million signals, because each device has several hundreds of signals that we can generate. So all of these all this power that we have to manage is controlled by a dedicated control system that is made in many layers. This is a picture that I like, was on a spot on a commercial back in time when I was a kid, and give an idea. This guy is Carl Lewis, is one of the most successful runner in the history, we can say, in the 100 meters, 200 meters, in the relay for 400 meters, long jump. He won everything, but the advertisers say that if you do not have control, all this power is useless. And our control, this is our sight from top, and the control is divided in several layers. Let's say from quite fast control that is based on FPGA and enters to protect the machine, basically. We have even another control that is for personal safety, but that one is, let's say, separate by all of these. The FPGA is to protect the machine because the beam goes to the speed of light. I don't have to tell you, most of you are particle physicists, so you know. And so we need a very quick system to protect the accelerator if we have some loss, if we lose the superconductivity, or if we have some other issue. Then there is a slow system of control that is the one used by the operators, and mainly our coding, our Python coding goes there. So the main interface that we have is EPIX. EPIX is a protocol that was invented, I think, in the Argonne laboratory. Here are some of the participants. I think it's from the Argonne. And that protocol is an abstraction of all these signals. It's based on what we call IOC, or can be PLC, or can be FPGA, or can be some Linux machine. And then the protocol is abstracted and it's transported through a network to the system that archive data, search for data, analyze the data, and makes other data analysis live. The main role of the main activity that I do in this lab is to do the online activity for the accelerator. It means to simulate the accelerator when it's live, to suggest to the operator what to do and how to help the operator to change the parameters of the machine, working directly on the control system. For this reason, we use several tools, but Python is a large part of it. Then the next part that is for Python is the data analysis, so online and offline. And I go now with a few examples of these that I want to show you. And I will try something that we should never try in a real life, because you know, whenever you want to run some example, in general it fails. So what I run here is really from our control system right now, and I hope it will work. If it doesn't work, is because as any demo, when you try to show things, in general it shouldn't work, because this is how computing is in real life. So if you have questions, stop me, ask me. There is no, we can have even some conversation. What I show you now is something that I use very frequently. And I want to show you because it's a quite strange use case. As you can see here, I use JPype. I don't know if you are familiar. This is a Java to Python interface. It uses the Java native environment to communicate with the Java protocol. That is the reason why I had in mind this example of NumPy interacting with another code, because I use it very frequently. What is in Java here? We have these classes that are from a simulator. We call it OpenXIL. OpenXIL was invented at the Spallation Neutron Source in Oak Ridge, and we reuse it because it's integrated already with EPICS, so with the protocol that we use to control the machine, and is in Java. The reason why we stay on Java, it's because the other part of our control, of our interface to the control, is Control System Studio, and is done in Java, so we can have some interaction. And also because originally the OpenXIL, this suite that does simulation of the machine, was written in Java at the Spallation Neutron Source. So we collaborate with them, we improve the model, we create our own model. The model that we use here, I mainly created with a colleague at ESS. And what we do here is that we use it, but from Java virtual machine. So in this way, we can create a virtual machine that is now running in our Jupyter, that is remotely hosted on our machine. And from here, I can simply load our particle accelerator and start to see the components of our accelerator. So here you can see from Python the structure of the machine that comes from the Java simulator. This is a double object. OpenXIL works as Java simulator and as a control of the EPICS. So when we have an element that can be, I don't know, a magnet, the magnet can have its simulation code. In parallel, it has also the control code with all the names of the variables that we can control. In this way, we can switch from offline to online model continuously. We can instantiate the online model with the variables that are from the machine and then run offline the result. That is what I will show you, because the machine is down because of installation right now. But I will show you a simulation of a sequence of our machine. And then in theory, you can apply the results of your simulation, of your change of magnetic field, electric field, or whatever, to the real machine. So for example, here I load the MEBIT sequence, medium energy beam transport. Among this sequence, you can identify that there is one sequence called MEBIT. And then here I can see the sequence. These are quadruples. These are vertical corrector, horizontal corrector, beam position monitor, accelerating gap. In this case, are not accelerating, but rebuncher, etc. So from these, for example, I want to see only the quadruples, and I can extract them, and then I can see if one quadruple is really a magnet. Yes, I have a lot of method that comes from the simulator, and I can access all in Python. So this is very practical if we want to prototype and work with the simulator from the control room or even from home, as I am doing now. And then I can check what are the channels to read and write values to the machine. So these objects here are connected to the machine, and I can change the value of the magnetic field on the machine. From home, I cannot, because I need the right permit, and is forbidden in this way that I am showing. But in general, from the control room, this is possible. Then let's say I want to run a simulation. Here I skip the syntax here, but simply what I generate is I take the sequence, I give initial condition of my beam that I call it probe at the beginning of that sequence, and then I set up the parameters in terms of energy, emittance, current, and all the parameters that define the shape of the beam in 3D. I create a scenario where a scenario is the sequence and the beam. I say if I want here design that is offline or online, I can switch here, and then I can think the model and run it, and it's done. And now I propagate the beam along my sequence. And as you can see, is 1 second. This is my job, basically, to identify all the possible approximation to the physics to make the code running at this speed, because the operator doesn't want to wait 1 week to have the result of the simulation, want to have something quick. Then I can get back my probe, that is the beam, and for example, I can plot it. This is the size of the beam in X, Y, and Z. And on top of this, for example, one thing that is quite interesting with Python and Jupyter especially is that we can do it interactively, for example. And now I rerun the same thing, but the magnetic field of the quadrupole that I choose now is the variable that I decide to choose here with this simple slider, so I can change it, and I can change the size of my beam with my magnetic field. So I am really changing the knob of the magnetic field of one magnet and see the effect on the beam. On top of this, I can even visualize the beam. This is the 3D of 1 sigma of the beam. So I can go here and decide to focus more on the Y plane or defocus it and make it exploding, because I am totally mismatched now because the field is gigantic in the other direction, and I can inflate my beam and see how is in the end of my sequence. So the operator have the ability here to create its own code, its own little simulation with very little code. Is nothing, it's more for plotting than for executing the simulation, and interact with the machine, create a setup that he likes, and then apply to the accelerator. This was the first thing that I wanted to show, and was at the beginning why we wanted to have some code in Jupyter to prototype thing quickly. Then in doing this job, I need to interact with the variables of the machine. When I say here, these are the name of the magnets, where I have it is before. Here. These names are quite complicated, and there are 10 millions of it, or there will be 10 millions of it. I have a question here. Did the speaker develop the Python-based accelerator simulate code? Under the impression many are written. Okay. The question is, did the speaker develop the Python-based accelerator simulation code as well? I have the impression that many are written in Fortran or C++. Is this a Python wrapper? This is a Python wrapper or communicator with Java. And here the code is in Java, the one that I show you. I have also some simulator in Python. You are right, a lot of accelerator code is in Fortran and C++. The most successful one is MADX from CERN, and is a blob of C, C++, Fortran, and Python all together in something that is totally impossible even to understand. I was one of the maintainers of that blob, and believe me, it's horrible. But it works. It generates physics that is correct, so people tend not to change those things. So I continue here. What I was saying is that this name can be very complicated and can be many. So this is the problem that I found, and it's the reason why I'm here. One problem is to identify the right name of the device, and this create, we have a database for it. But when we browse the database, for example, these are the oxygen monitor. I use these values because I know that are active on site, so we can see some real value. And here you can see that we have a lot of these names everywhere. When I search for a name, and then I have to remember that is ODH, oxygen depletion hazard, minus O2. The I has to be small, the M has to be capital, -2, column, con with the C capital, S big. So it's a nightmare to remember those names. And this is a very, very small part of our devices. So how we can do to help the user? This was my question originally to Matthias, because I tried to use the API of Jupyter to do the autocomplete for these names, and I failed with the column and with the special letters. So in the end, we end up to this workaround. I can explain it, but I think if I give you the code is even better. And the result from this is that now I have simply a system here where I can autocomplete the name of my object. And this is presented in blocks because it's gigantic, the database, but I can search sequentially here. And then I have, for example, the M1, and then I can search, and I want to see the level of oxygen that we have in our lab, and hopefully is 20% of the atmosphere, 20.8, because we know that oxygen is around 21. And so this was mainly the part of code that I needed to help the user. Now this is fully integrated in our Jupyter, so every time you start something, you can complete with the name of the variables, and you can use them if you need to know exactly which object you are looking for as string. This is connected to our database. It communicates, get the first part of the name, and gives everything to the user. And this now is very valuable, and we are using in all the system basically. So that is the second example of Python that is pure code here. The functionality in terms of physics is nothing, but is purely a code to help the user to get the variable of the machine quickly and in a safe way without typing all the capital and small letter. And then the last thing that I can show you in Python here is a completely different thing that is not a simulation, is not is not pure code, but is data analysis. That is the third big area where we use Python. In this case, what I show you is something that we did recently. We published a paper on it. Basically, we from the RFQ, the radio frequency quadrupole, the first object all in copper that I show you, we started to put some power without the beam, but we wanted to know the acceleration of this device, how much field it generates. And without the beam, we have no instrumentation inside. So what we did was to exploit the fact that while you power it, some electron is released inside. The electron travel inside the device, hit the object, and generate an X-ray. And the energy of the X-ray tends to be the energy of the acceleration. So from, or the voltage, let's say, so from the device that, from powering the device and from these electrons that are generated by the surface, we were able to estimate from the energy of the X-rays released outside the device, we were able to estimate the power of the device. And here is all the calibration of the X-ray device, and then the data that we acquired for months. And then I created a simple interface to read the file that comes from the instrument. And from this file, we can, for example, set up some parameter here and there and have a plot that gives the raw data of the count of the energy of the X-ray released by the device, by the electrons inside. We can average it and the slope is the Bremsstrahlung of energy from the X-rays generated from the electrons, and the limit of the linear part is more or less the energy of our device. So we know, for example, here that we were accelerating at more or less 99 kilo electron volts. And this gives us an estimation if our device is powered correctly or if there is some failure inside, because if there is some failure, the electrons inside accelerate less. So it's an indirect measurement of our object without exploiting any measurement device of the device itself. We were using an external X-ray monitor. This is the device that was powered. The electrons were released here inside the chamber. And then the X-ray device was put outside here. This is the RFQ. So this is exactly the same that you see here in cross-section. And then the X-ray were collected by this device and analyzed through our Python interface. And with Jupyter, it's very easy to do simple interfaces like this, browse a different file and reuse the code. In this way, you can tweak the parameters here, for example, and try to find the best fit. And once you have an idea, you can do some model that is a bit more detailed. So this is more or less how I use. I can show you many examples. I have our public screen. This that you see is completely a backend in Python that generates the signals in JSON format. For example, we can return to our oxygen monitor, the one that you saw before in the Python Jupyter. And these values are real time. They are generated by the control system through epics. There is a Python interface that collects them, generate a JavaScript, and then this JavaScript generate a JSON, and this JSON feeds a JavaScript that display the values on our public screen. And we have a set of these screen for many things here and are all controlled by Python. I can show you the RFQ, the water temperature of the last 2 weeks in our water-cooled device. For example, one thing we can see is if I set 2 days, you can see from our archiver database that the temperature of our water goes up and down depending on the moment of the day, because of course during the night everything is colder, and even the water, even if it's stable and controlled, even the water has some change between 23.75 to 24 degrees. So you can see when it's night and day in this weird way. So Python is ubiquitous to our system, and it's really everywhere in our daily life. All the tools that you see here that I presented here, more or less I wrote them. So to answer to the question how much Python, you can imagine I have also a notification system that is all the backend is written in Python, then the application are written in mobile, Swift or Java or whatever. So this was more or less what I wanted to present. Then I was not exactly sure about what was your interest. So I am open to a discussion, question, or whatever you want to know about our particle accelerator.
Yeah, thank you so much, Emanuele. And I'd like to invite our panelists back up and open the floor for any questions that you may have.
That web interface that you showed at the end was really cool. It's neat to see modern tools mashed up with epics that's been with us since the late 80s or early 90s, depending on how you want to count it.
Yeah. Well, epics for me was the real painful thing, because we started with the epics 3, and it's really a nightmare to have it running properly, especially outside the technical network. So to the gateway, as they call it. The gateway are really objects very old in the structure, and they hangs every time someone is throwing too many data. Are really crap piece of code, I would say. Then we migrated to EPIX 4, that's now they call 7, because there is this backward compatibility between 4 and 3, so they say 4 plus 3, that becomes 7, and it's a mess in the numbering. But we use
it's a
EPIX
Fibonacci
7.
series-based versioning scheme, I guess.
Exactly. Yeah. So it's called 7, but it's EPIX 4 and EPIX 3 together. And that one is much better. Everything here is now EPIX 7, let's say, and it's the level of stability improved significantly. So I can show these things, and I'm quite sure that it doesn't hang, crash, etc. It's quite stable now.
This is a little bit of a technical question, but when you moved to 7, were you still using channel access, but version 7 of it, or were you using the new so-called PV access protocol?
It's everything on PV access. I use the library P4Pi. That there are two concurrent main implementation, let's say, in Python. I use P4Pi, and I think it's quite good. It's still not probably mature as it was PyEpix, but even PyEpix was because PyEpix was using a bridge with the C libraries and was quite broken when the dataset was too big and fast. So P4Pi is entirely Python, is purely Python protocol EPIX, and is PV access. And it's great, especially because we work even with tables that are complicated objects now that we can implement in EPIX 4 specifically. For example, the timing of our machine is designed as EPIX table now. So we use everything in PV access.
One last question about the web demo. Did you say JSON was generated by the backend or Jython? I couldn't tell which word you said.
JSON, I can show you.
Okay, that makes more sense.
Give me a second that I can show you how it works, this system. I go back to share my screen. So let's do for the oxygen that is a live measurement. This is the source of the page. And then this is our very simple URL. And this is the result of this URL. I implemented really a translation between the get and the page. Here you can find the values that you see in the oxygen monitor. So you have all the values here, and for example, this monitor has the value of 20. Can you? It's okay. The screen. Can you read it? Yes. And you can have the timestamp and everything. All the details of that variable is presented as JSON, and then the front end is analyzing this data and producing the page.
Emanuele, I have a social question. When you introduce yourself, you say, I'm a physicist. You don't introduce yourself as a programmer. But the things that you've showed us here are very technical, very sophisticated artifacts of programming, dashboards, the use of IPy widgets and completions in Jupyter Notebook. When you bring on a new person into your lab, maybe a postdoc or another scientist, and they have that same attitude of, I'm a scientist, not a programmer, how do you motivate them to be willing to do things at a level of sophistication that you showed us?
This is a quite complicated question in the sense that, well, there is a thing. I am by studies a physicist. I am even a theoretical physicist in my master. Then I did accelerators for the PhD. But I started coding when I was 8 with the Commodore 64. You know, probably other people here started with basic Commodore 64, playing with the Amiga. learning C from Kerning and Ricci with a very old Intel machine, etc. So coding was along the way all the time, coding, hacking. I wrote even kernel modules when Linux was out in the beta. So I have a background that is a bit strange because I don't know how to give this to a student or to a postdoc. It's complicated. But my idea is that in theory, coding should be done by professional coders today, because probably when I started and when an entire generation of physicists started, they were also the coder. Today, there are professionals that studied how to code, and in general, I tend to prototype and then to give to some expert to make it clean and to maintain it and to use it properly. Then this is a mixed job, because if I know how to do something, I tend also to implement it. So it's difficult. What I try to do is to assist someone that starts to write the code and try to help and see that things are done in the correct way. But then my attitude is always, look, ask to the expert. Try to stay on track, not start with a broken window. Try to make things step by step. And when the code starts to become quite big, it's better to have a review on it. But then, you know, the process is always complicated. The line between physicist and someone that starts to write professional code is very, very tiny, and it's very easy to cross in all the directions.
You basically convey to them that, look, you're going to end up having to do this anyway, might as well figure out how to do it right, figure out how to, you know, come to terms with it.
Yeah.
Fantastic. Any other final questions before we get wrapped up here? I notice we are at time.
I would have one question. It's like, how do you run your infrastructure? So is it the Jupyter notebooks, were they running on your laptop, or is this like a central server where many people interact, like Jupyter Hub, or how do you do this on the Python side?
At the moment, the one that I show you is on our infrastructure, so it runs in our data center and is a Docker where there are images for each users. So I am isolated in my Docker. I can do whatever I want. The resources are allocated to me, and then I share the real machine with other people, and there are several virtual environments where the user can play around. Then I have also a local installation if I need it for prototype on my laptop. I also use Jupyter on the machine. But let's say that this instance that you saw is a duplication between technical and public network. So on public network, I can do exactly what you saw. And I have an exact copy of what I did in the technical network. And when I am in the control room, I can use it and even write on the PV. So I can play with the real machine. But that is isolated, and only the file system is duplicated in the way that I have the same Jupyter. So I can prepare it at home, in the office, whatever, and then I can go in the control room and execute it in the real machine.
Okay, very interesting.
With access control and everything.
Thanks for sharing. And we do have one final question from the audience, and this was in the event chat. It says, "Hi, Emanuele. I was wondering how you built the interface. It looks like real-time operating data saved in JSON." And they guess that their question is, how was the interface or front end built? Is it HTML and CSS or built using some other Python package?
Okay. Probably you mean the public screen, the greenish one, is correct?
That's what I'm envisioning, but I'll let you know if they respond.
Well, I assume that one and start to answer, but I guess it's that one. So the idea is the backend, and this was one of my comments to James that in the end I forgot to say. When you use function, one reason to use function is, is when you have callback function. So Epix and the library in Epix has the possibility to use callback for updating the values. The reason is that in Epix, you can be a client that is polling and asking to the server if there is a new update, or you can subscribe to the server and the server send you back the information whenever one of the variables that you subscribe is updated. This is called monitoring. And the interface that you saw in Python is monitoring. So the Python code listen for the variables and monitor them and store in a local database that is updated every time that something in the network is updating. So the Python part has a database updating, and then it shows the JSON whenever it's requested, and each variable is reused. So if many pages request the same value is calculated, it's requested only once and then broadcast to many. There is quite a lot of work to make it efficient. Then the front end is loading every 10, 20 seconds, I don't remember, the query, is doing the query to the Python client every couple of seconds, passively, let's say, every time that there is a JavaScript that does the load. The interface is a cheat. I am using Freeboard because I am a lazy bone and I don't want to put my finger in JavaScript because I hate JavaScript. Sorry, I know that here there are people using it, but I really cannot. I hope I will die before I have to write JavaScript professionally. And I write some JavaScript because to maintain this interface I do, but the minimum that I can, so is like Grafana, but a bit more flexible. And simply, there are widgets. You can code them. You have to change very little. And there is the engine in JavaScript that does everything. So I load the value, I display as a light or a gauge, plot, whatever, and then I show it. If you want to have the full thing, you can write me, and I can give you the Git repository with all the code. It's everything public, what I show here.
Fantastic. Thank you so much, Emanuele. And thank you for sharing all that you did with us today and how you use Python and Jupyter in your environment. Looks very snazzy. I'm sure we've received a number of comments saying how nice that dashboard interface looked. Before we wrap up, I did want to remind everyone that you can find more information about our upcoming exchange as well as the video from today's exchange on our website. That's meetup.doepy.org. And I did want to tease you a little bit because next month we'll be joined by Todd Gamblin from LLNL, who will be sharing about a project he works on called SPAC, a package manager for supercomputers. With all that takes us to the end of our time today. I had an absolutely wonderful time, and I think I can speak for all of our guest panelists that we all enjoyed ourselves as well. I'll see you all next time.